So in this video, I'd like to go over the definition of a conservative field. There are several definitions we can define a conservative field, but in my lecture notes, I used an integral definition of a conservative field, but in the lecture, I actually discussed something. I defined a conservative field in terms of a gradient function. So what is a conservative field? And specifically, I'm looking at a force field. So a conservative force field is going to be if we can construct a force field F, where is a function of x and y and z. So it is a vector field. And if I can write it in terms of the gradient of some scalar function, then we say that F is a conservative force. Now, I didn't want to confuse you guys right away, right? But we can actually show that from this definition, right, that if we have a scalar function and it's a specialized function, it's connected and it's also smooth, we can actually use Stokes' theorem, right, to show that the path of any, the full path, any closed loop path, right, coming back to the same point, the work done is actually equal to 0. So actually I could prove this, but I didn't want you to get confused in that. So in the lecture, I actually defined this to be definition of conservative field. The potential function, this is called the potential function. Or the potential energy if you want, but this is called the potential function. So for example, if phi is equal to x squared y and z, and I'm calculating the force field, so whatever the force field is, so we're going to calculate it as the gradient of this. So I'm going to assume this is a potential function or potential energy function. Mistake. This is a potential energy function or a potential function, or simply just potential. So this potential, right, is given by the gradient, so I can write this off as minus the partial of, let's do this. So remember, this is the gradient operator, which is I partial of x. So just remember, I'm assuming x, y, and z are independent of each other, and because of that, right, I'm not explicitly writing partial of x, y, comma, z, which is a better notation, but the problem is it's a lot of writing. So we're just going to write that x, y, and z are independent variables. So here's our operator I, j, partial of y, plus k, partial of z. And these are operators, all acting on phi, which in this case happens to be x squared, y, and z. So the first, we take the partial with respect to x with a minus. So this is minus I. Partial of x is 2x, y, and z, minus j. Partial of y is x squared and z, and k minus k. Partial of z is x squared y. So this force field is called a conservative field. So now let's do some examples of this so we can actually construct conservative fields. So it's in my lecture notes to explain the exact details of where everything's coming from, but in class I actually try to simplify it a lot by starting with this because it's easier to understand gradients than it is to start talking about path integrals and looking at connected spaces and whether the space where the potential function is smooth in some region and well, whatever. It just takes too much work to explain those details, so it's easier to actually understand in terms of the gradient function. There's actually several definitions we can actually say for conservative force, and I use the integral definition. So actually, let me explain what that is. So we can actually show for a special class of functions, and I have to assume something that if a force field is conservative, either by this definition, or we can actually say that the work done in any closed loop path gamma, if we're doing closed loop path, that's equal to 0. So I can start with this definition, assuming connectivity in the space and stuff, but those explanations are quite long. But this is the definition that I used in my lecture notes. But this is the notes in lecture. I actually did this with terms of the gradient. They're both equivalent to each other. On special, there's provisions, for extra provisions, but connectivity and stuff, but let's not go into those details. But the main thing I really want you to do is feel comfortable with using a gradient operator of the scalar function, and the negative of that is actually to find the force. Make sure it's a minus. So if there is a minus, then we call this a potential function, the potential. And so let me give you examples of this. So imagine that we're told so testing of a function. So you might get lucky, but let's imagine the following example. So you're given a force field of x squared I plus y cubed j plus z to the fourth k. And I want to know if it's conservative. Now we could actually check this by taking the cross products, which is in my lecture notes, but I want you to feel comfortable doing this. So instead, I'm going to assume that there is a gradient function, phi, such that this is equal to true. And the question is, how do I find the potential function? Phi. So to do this, right, we just expand, and so we know the definition of the potential function, right, means that this is equal to minus the partial of x with respect to phi I, expanding the gradient operator, minus the partial of phi with respect to y, j, and minus the partial of phi with respect to z and k. And if you equate them, right, we're getting three different equations. They're saying that minus the partial of phi with respect to x is equal to x squared. And we're also told that the j components are equal, so partial of phi with respect to y. And just remember, okay, whenever I'm using the gradient operator, I'm automatically going to be assuming that x, y, and z are independent. And so these partial derivatives I'm writing is just contracted notations. I'm really emphasizing this because you will make mistakes when you do statistical mechanics class. So be careful on these things, okay? So we're assuming that x, y, and z are independent. In a lot of your math classes, you automatically assume it, but we can't assume that in a lot of our physics classes, because some variables are independent of each other, others are dependent on those independent variables. So you have to be really careful. So in this case, right, let's continue, minus partial of e is equal to y cubed, minus the partial of phi with respect to z is equal to z to the fourth. So basically I'm saying that the partial of phi with respect to x is equal to minus x squared. Partial of phi with respect to y equals minus y cubed. And partial of phi with respect to z is given by minus z to the fourth. Now, we can actually test if there is such a potential function, that whether this function is conservative, by taking something called the curl of this function of the force field. So I could calculate the curl of this, and if it's equal to 0, and assuming that the space isn't connected properly, and it's a nice space, a nice looking space, three-dimensional space is okay, then we can actually say that there does exist a conservative function, and then I can actually take any point in the space and integrate it. And that's the example in the lecture notes. But to simplify things, because I don't want you to kill yourself in understanding the ideas, and you might not fully absorb all of the integral equations that are in the lecture notes. So I'm just doing it in terms of partial derivatives. And so the question is, if I had a partial function phi and I took a derivative, I get minus x squared. I know that this must mean that phi is probably the negative one third of x cubed plus some function of y and z. Because remember, if we go backwards, if I take the partial with respect to x, we'll get back minus x squared. Okay, notice that since y and z are held constant, because that's what I meant by x, y, z are independent variables, right? Then we would see that this would be 0, the partial of f, y, z. So there's a function out there that I don't know, but this integral equation says that I can take the partial derivative equals this. And so I can repeat this process for the partial derivative of y with respect to, phi with respect to y equals my, and I can say that, well, therefore phi most likely is taking the antiderivative of this, so this would be like y to the fourth minus divisible by 4 plus some function of x, f2 function of x and z. So I don't know what this is, but if I go backwards and take the partial derivative of phi with respect to y, you'll notice you'll get back minus y cubed. So it looks like an antiderivative, but I have an extra constant. This constant, right, well, it's not a constant, it's a function of the other variables. If we were doing antiderivatives in like first year calculus, right, you'd see that this would be a constant, but these are not constant, these are functions. So this implies the same principle. We can say that phi is equal to minus z to the 5 divisible by 5 plus some function of, we'll call it function 3, consisting of x and y's. So generally, each of these partial derivatives gives you some kind of a structure in phi. And the question is, if you look at it carefully, right, if f1, right, is really, it has to be a function of y and z. If this is y and this is z. So if this f1, right, is actually y to the fourth 4 minus z to the 5 over 5, and f2 is really 1/3 x cubed, they overlap. And the net effect is, we could say that you can actually see that phi could be minus 1/3 x cubed minus, so this terms, this procedure doesn't generally work, but you might get lucky in solving this. In this case, I was very lucky, and there's a better procedure for doing this. So the better procedure is a little more complicated. It's in the lecture notes though. So some constant. So if I think about it really carefully, you'll notice that if I take the gradient of this function, the negative of the gradient of this function, you'll get back the original equation. So because I've actually shown the function, right, I can say that f is conservative. Therefore, I'll go backwards. Therefore, f is a conservative field. So this conservative field, right, means that, well, because I found the potential function. So I'm saying it's conservative, not because I did some weird calculations. I actually found the actual function. Because I found it, I got lucky. So you might be able to do it this way. You might not be. You might have a conservative field, but might not be able to construct the potential easily. In which case, the better way of doing it is in the lecture notes, where you actually show that. So the idea being that if you know that the path, right, if the path doesn't matter, actually, you know what, it's in the lecture notes, and I don't want you to spend time thinking about it unless you ask me in class again. Anyway, so f is a conservative field if you can actually show that you can have a potential function and the negative gradient of the potential function is f, then f is a conservative field. And so one of the examples that I want to make sure you understand, right, is when we're dealing with springs. So imagine the following scenario, and we'll need this for when we're dealing with Lagrange equations of motion. So imagine the following case. I have a spring, and this spring, right, is attached to a mass m. So it's got a spring constant k. We remember that if this is at equilibrium and we displace the spring by a value of x, and I'm going to actually assume from this coordinate system, right, my origin of my coordinate system is along x, and I'll assume y is up and coming out is z, to make it really simple and obvious. So here's our spring, and it's a one-dimensional object. It's on a frictionless surface, so we're not going to be worried about whether it's got friction or not. Let's not worry about things like that. But specifically, I know if I pull this object, right, and displace it, I know that the resulting force, the force of restoration by the spring, right, let's call it Fr, is given by the spring constant by x. And one of the first questions we should ask ourselves, right, is this field for any value of x, right, assuming that it's y's and z's don't really matter, that this force field, right, that is in 3 dimensions. It just happens to be in 1 dimension, really. But this force field, is it a conservative force? And so one way of showing it, right, is it's a conservative force if I can show that this force can be written as the gradient of some potential function, phi. So I'd like to find it. So, and because I'm putting this restoration force, and I forgot this is a vector and this is not, so I'll put the directional directive in. So this along the x is the I unit vector, j vector, and k vector. So I want you to think simply. So one way of looking at this restoration force, right, of the spring force is basically k is the spring constant, and x is the displacement from equilibrium. Okay? So can I write this in terms of a gradient function of phi? And so we're going to go back and say, oh, you know what? I know from definition that this is really partial of x phi I minus partial of phi with respect to y j minus the partial of phi with respect to z k. And we start equating them together, and you'll actually see that the first value is partial of phi with respect to x is equal to kx. Then you have partial of phi with respect to y is equal to 0. There is no j component. Then the partial of phi with respect to z is equal to 0. This is not the preferred technique for calculating if it's conservative, but if we can find the phi, then we know F is conservative force. So that's what I'm trying to do. I'm trying to find phi, even though this is not the preferred way. The more exact way is a little more complicated, but I'm going to try to find phi. And so to do this phi, right, I can actually say the antiderivative of phi is basically phi in the first example, right? I'm just looking at this and not worrying about y and z, so that the antiderivative would be kx squared over 2 plus some function of y and z. How about the partial of phi? Well, the integral of 0 is equal to, well, it must be some function of x's and z's. And then this says that the antiderivative, or the anti-partial derivative, must be some function of x's and y's. And for all these three to match, right, if you think very carefully, right, so we can actually say that, phi is equal to kx squared over 2, which is the elements that's here. There's no y, there's no z. And so plus a constant, a physical constant. So this is called the potential function, or simply potential. Ooh, can't spell potential. Okay, so I have the potential function, and now let's go back. I know if I take the gradient of phi, and if you plug it in, right, you'll actually start seeing that you'll get back minus kxi. So therefore, we can conclude that Fr is a conservative field, and more importantly, the potential function I need, right, is kx squared over 2. And that's kind of important to us, right, when we start talking about Lagrange-Euler equations, right, or the Lagrange equations of motion. So I need a potential function for a spring. It's actually kx squared over 2. Now there's a better way of doing it with f dot dr, but a lot of people do this, and I want you to do it in terms of the simplest ways of your understanding of well, derivatives and partial derivatives and stuff. So this equation right here, kx squared over 2, we're going to need this a lot. So conservative fields, so now we do springs. Later we'll do more advanced techniques where I'll start looking at force fields that are radially dependent on, anyway, let's talk about it another time.